Strange voltage readings on a transformer secondary can stem from several potential issues. Firstly, inspect for loose or corroded connections. This includes scrutinizing the secondary winding connections to the panel and all grounding connections. A damaged transformer is another possibility, potentially leading to imbalances in the secondary voltage readings. Faulty grounding plays a significant role, as the absence of a ground wire can create incomplete grounding paths, causing voltage imbalances. Another factor to consider is load imbalance. If the load on the panel isn't evenly distributed between the phases, it can result in unequal voltage readings. In the case of ground fault interrupters, GFIs tripping, this typically occurs because they detect an imbalance in the current flow. When one phase exhibits no voltage to ground, the current from the other phase flows through the neutral wire and returns to the transformer through the affected phase's winding, causing a current imbalance. To diagnose and resolve these issues, follow these steps. 1. Check all connections. Tighten any loose connections and clean any corroded terminals. Ensure all wires are properly and securely connected. 2. Test the transformer. Use a voltmeter to measure the voltage across the primary and secondary windings of the transformer. Compare these readings with the known expected values to determine if the transformer is functioning correctly. 3. Establish proper grounding. Install a ground wire from the transformer to a verified and suitable grounding point. This will provide a complete grounding path and help stabilize the voltage readings. 4. Check the load balance. Distribute the load evenly between the phases to avoid voltage imbalances. Employ a current clamp meter to measure the current on each phase. 5. If all other solutions fail to resolve the issue, replacing the transformer may be necessary. Remember, before undertaking any electrical work, ensure that the power is turned off and all appropriate safety precautions are observed. Now let's delve a bit deeper into each of these potential issues. When checking connections, pay particular attention to the tightness of screw terminals and the condition of wire terminations. Look for signs of corrosion, such as green or white deposits, which can indicate a poor connection. If corrosion is present, clean the terminals with a wire brush and apply an antioxidant compound to prevent future corrosion. When testing the transformer, ensure that you are using a voltmeter that is properly rated for the voltage levels involved. Measure the voltage between each phase and neutral, as well as between each phase and ground. Compare these readings with the transformer's nameplate voltage ratings. Significant deviations from these ratings can indicate a problem with the transformer. When establishing grounding, it is crucial to connect the ground wire to a suitable grounding electrode, such as a ground rod or a building's grounding system. The size of the ground wire should be appropriate for the size of the transformer and the electrical system. Consult the National Electrical Code, NEC, Table 250.166 for guidance on ground wire sizing. To check the load balance, use a current clamp meter to measure the current flowing through each phase conductor. Ideally, the current should be approximately equal on all phases. If one phase is carrying significantly more current than the others, it indicates a load imbalance. Rearrange the loads on the panel to distribute the current more evenly. If replacing the transformer becomes necessary, ensure that you select a replacement transformer that is of the same voltage rating, kV, kVAR, rating, and impedance as the original transformer. Replacing the transformer with one that has a different rating can cause serious problems with the electrical system. Here's a more detailed explanation of why a lack of proper grounding can cause problems. Without a ground wire, there is no low impedance path for fault current to flow back to the source. This means that if a fault occurs, such as a short circuit between a phase conductor and the metal enclosure of an appliance, the fault current will not be able to trip the circuit breaker or blow the fuse. This can create a dangerous situation, as the metal enclosure can become energized, posing a shock hazard. Ground fault circuit interrupters, GFCIs, work by detecting imbalances in the current flow. They compare the current flowing through the hot wire with the current flowing through the neutral wire. If there is a difference of more than a few milliamps, the GFCI will trip, cutting off the power to the circuit. This is because the difference in current indicates that some of the current is flowing through an unintended path, such as through a person's body. In the scenario described, the GFCI is tripping because there is a current imbalance. When one phase has no voltage to ground, the current from the other phase flows through the neutral wire and back to the transformer through the affected phase's winding. This creates a current imbalance that the GFCI detects, causing it to trip. To prevent GFI tripping, it is essential to ensure that the electrical system is properly grounded and that the load is balanced. It is also important to use GFCI protected outlets in areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor areas. Now let's talk about voltage imbalances in more detail. A voltage imbalance occurs when the voltages on the three phases of a three-phase system are not equal. This can be caused by a variety of factors, including unbalanced loads, faulty transformers, and loose connections. Voltage imbalances can cause a number of problems, including increased motor heating, reduced motor efficiency, and premature failure of electrical equipment. To measure voltage imbalance, use a voltmeter to measure the voltage between each phase. Calculate the average voltage by adding the three-phase voltages together and dividing by 3. Then calculate the percentage voltage imbalance using the following formula: voltage imbalance equals maximum deviation from average voltage divided by average voltage multiplied by 100. According to National Electrical Manufacturers Association (NEMA) standards, the voltage imbalance in a three-phase system should not exceed 5%. If the voltage imbalance exceeds this limit, it is important to take steps to correct it. This may involve rebalancing the loads, repairing or replacing faulty equipment, or tightening loose connections. Regarding load balancing, consider the following example. Imagine a panel feeding several lighting circuits and a few receptacle circuits. If all the lighting circuits are connected to one phase and all the receptacle circuits are connected to another phase, this would create a significant load imbalance. To correct this, you could move some of the lighting circuits to the other phase or move some of the receptacle circuits to the first phase. The goal is to distribute the load as evenly as possible between the phases. Use a current clamp meter to measure the current on each phase after making these changes to ensure that the load is balanced. Additionally, ensure the current draw from equipment and any installed devices, such as lighting fixtures, is properly rated for the specific voltage and current ratings. Next, let's explore some more advanced troubleshooting techniques. One technique is to use a megometer, also known as a megger, to test the insulation resistance of the transformer windings. This can help to identify insulation breakdown, which can be a sign of a damaged transformer. To perform a megger test, disconnect the transformer from the power source and connect the megger between each winding and ground. The megger will apply a high voltage to the winding and measure the amount of current that leaks through the insulation. A low insulation resistance reading indicates that the insulation is breaking down and that the transformer may need to be replaced. Another advanced troubleshooting technique is to use a thermal imager to scan the transformer for hotspots. Hotspots can indicate loose connections, overloaded windings, or other problems. If you find a hotspot, investigate the area further to determine the cause. When dealing with electrical equipment, it is always important to prioritize safety. Before working on any electrical equipment, turn off the power at the breaker and verify that the power is off using a voltage tester. Wear appropriate personal protective equipment, such as safety glasses, gloves, and insulated shoes. If you are not comfortable working with electrical equipment, hire a qualified electrician to do the work. Code 45.12. One crucial aspect often overlooked is the potential impact of harmonic currents on transformer performance and voltage readings. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as electronic devices, variable frequency drives, and some types of lighting. These harmonic currents can distort the voltage waveform and cause inaccurate voltage readings. They can also overload the transformer, leading to overheating and premature failure. To mitigate the effects of harmonic currents, consider installing harmonic filters. These filters are designed to reduce the amplitude of harmonic currents, thereby improving the power quality and protecting the transformer. Another important consideration is the transformer's K factor. The K factor is a measure of the transformer's ability to withstand harmonic currents. Transformers with a higher K factor are better suited for applications where harmonic currents are present. When selecting a replacement transformer, make sure to choose one with an appropriate K factor for the application. Furthermore, regularly inspect the transformer's cooling system. Transformers generate heat during operation, and the cooling system is responsible for dissipating this heat. A malfunctioning cooling system can cause the transformer to overheat, leading to insulation breakdown and failure. Check the cooling fans or pumps to ensure that they are operating properly. Clean the cooling fins or radiators to remove any dust or debris that may be obstructing airflow. Also, inspect the transformer oil level and condition. Low oil levels or contaminated oil can reduce the transformer's cooling capacity. Consider periodic oil sampling and analysis to assess the oil's condition and identify any potential problems. Remember that electrical codes and regulations vary depending on the location. Consult the local electrical code and follow all applicable regulations when installing, maintaining, or troubleshooting electrical equipment. Finally, document all troubleshooting steps and findings. This will help you to track the progress of your troubleshooting efforts and to identify any recurring problems. Keep a detailed record of all measurements, tests, and repairs. This documentation can be valuable for future troubleshooting and maintenance activities. Let's also consider the scenario where the transformer is feeding a subpanel with multiple circuits. In this case, it's essential to check the voltage at the subpanel as well as at the transformer secondary. A voltage drop between the transformer and the subpanel can indicate a problem with the wiring or connections between the 2 points. Use a voltmeter to measure the voltage at both locations and compare the readings. If there is a significant voltage drop, inspect the wiring and connections for loose connections, corrosion, or undersized conductors. Correct any issues that you find to reduce the voltage drop and improve the performance of the electrical system. Furthermore, consider the impact of voltage fluctuations on the transformer and the connected equipment. Voltage fluctuations can be caused by a variety of factors, such as changes in the load and the electrical system or problems with the utility power supply. These voltage fluctuations can stress the transformer and the connected equipment, potentially leading to premature failure. To mitigate the effects of voltage fluctuations, consider installing a voltage regulator. A voltage regulator will maintain a stable voltage supply, even when the input voltage fluctuates. This can help to protect the transformer and the connected equipment from damage. In addition to the above troubleshooting steps, it is also important to consider the overall condition of the electrical system. A poorly maintained electrical system can contribute to a variety of problems, including voltage imbalances, ground faults, and transformer failures. Regularly inspect the electrical system for any signs of damage or deterioration. Replace any worn or damaged components, such as wiring, breakers, and outlets. Keep the electrical panels clean and free of debris. By maintaining a healthy electrical system, you can help to prevent problems and extend the life of your equipment. Another crucial aspect is understanding the transformer's nameplate data. The nameplate provides important information about the transformer's voltage rating, kVA rating, impedance, and other specifications. This information is essential for troubleshooting and maintenance. For example, the impedance of the transformer affects the fault current level. A transformer with a lower impedance will have a higher fault current level, which means that it can deliver more current during a fault condition. This can be both beneficial and detrimental. On the one hand, it can help to trip the circuit breaker or blow the fuse more quickly during a fault. On the other hand, it can also increase the stress on the electrical system during a fault. Understanding the transformer's nameplate data will help you to make informed decisions about troubleshooting, maintenance, and replacement. Regularly inspect the area around the transformer for any signs of oil leaks or other problems. Oil leaks can indicate a problem with the transformer's cooling system or internal components. If you find an oil leak, investigate the source and take steps to repair it. Also, look for any signs of overheating, such as discolored paint or a burning smell. Overheating can indicate a serious problem with the transformer that needs to be addressed immediately. Don't forget to check the surge protection devices in the electrical system. Surge protection devices, SPDs, are designed to protect electrical equipment from voltage surges caused by lightning or other events. If the SPD are not functioning properly, they will not be able to protect the equipment from damage. Regularly test the SPD to ensure that they are working correctly. Replace any SPD that are damaged or have reached the end of their service life. Finally, remember that electrical work can be dangerous. If you are not comfortable working with electrical equipment, hire a qualified electrician to do the work. Always follow proper safety procedures and wear appropriate personal protective equipment. By taking these precautions, you can help to prevent accidents and injuries. Let's consider another potential issue: a loose neutral connection. A loose neutral connection can cause a variety of problems, including voltage fluctuations, flickering lights, and equipment damage. It can also create a dangerous situation, as it can cause the voltage on different circuits to become unbalanced. To check for a loose neutral connection, turn off the power to the circuit and use a voltmeter to measure the voltage between the neutral wire and ground at various points in the circuit. If you find a high voltage reading, it indicates a loose neutral connection. Tighten all neutral connections to ensure that they are secure. In addition, consider the impact of electromagnetic interference (EMI) on the transformer and the connected equipment. EMI can be generated by a variety of sources, such as radio transmitters, cell phones, and electronic devices. EMI can interfere with the operation of electrical equipment and cause inaccurate readings. To mitigate the effects of EMI, consider installing EMI filters or shielding. These devices can help to block or reduce the amount of EMI that reaches the equipment. Also, keep electrical equipment away from sources of EMI whenever possible. Regarding the grounding system, verify that the grounding electrode conductor (GEC) is properly sized and connected. The GEC connects the grounding electrode to the electrical system. It provides a path for fault current to flow back to the source, which helps to trip the circuit breaker or blow the fuse during a fault. The size of the GEC must be appropriate for the size of the electrical system. Consult the NEC to determine the correct size of the GEC. Also, ensure that the GEC is properly connected to the grounding electrode and to the electrical system. Loose or corroded connections can impair the effectiveness of the grounding system. Another important consideration is the type of loads that are connected to the transformer. Certain types of loads, such as motors, can create voltage sags when they start up. A voltage sag is a temporary drop in voltage that can occur when a large load is suddenly applied to the electrical system. Voltage sags can cause problems with sensitive electronic equipment. To mitigate the effects of voltage sags, consider installing a soft starter or a variable frequency drive (VFD) for motors. These devices can reduce the inrush current when the motor starts, which minimizes the voltage sag. Also, consider using a dedicated transformer for sensitive electronic equipment. A dedicated transformer will isolate the sensitive equipment from the rest of the electrical system, which can help to protect it from voltage sags and other disturbances. Regularly inspect the transformer bushings for any signs of cracks or damage. Bushings are insulators that allow the conductors to pass through the transformer enclosure. If the bushings are cracked or damaged, they can leak oil or allow moisture to enter the transformer, which can lead to insulation breakdown and failure. Replace any damaged bushings immediately. Consider installing a transformer monitoring system. A transformer monitoring system can provide real-time data on the transformer's voltage, current, temperature, and other parameters. This data can help you to identify potential problems early on, before they lead to a failure. A transformer monitoring system can also provide valuable information for optimizing transformer performance and extending its service life. Check the transformer's tap settings. Transformers have taps that allow you to adjust the voltage output. The tap settings should be set to provide the correct voltage for the connected equipment. If the tap settings are incorrect, it can cause overvoltage or undervoltage conditions, which can damage the equipment. Consult the transformer's instruction manual to determine the correct tap settings. Regularly inspect the transformer enclosure for any signs of corrosion or damage. The enclosure protects the transformer from the environment. If the enclosure is corroded or damaged, it can allow moisture or other contaminants to enter the transformer, which can lead to insulation breakdown and failure. Repair or replace any damaged enclosure components. Finally, keep the area around the transformer clean and free of obstructions. This will allow for proper ventilation and cooling. It will also make it easier to inspect and maintain the transformer. Remove any debris, such as leaves, dirt, or snow, from the area around the transformer. Also, ensure that there is adequate clearance around the transformer to allow for safe access for maintenance and repairs. Also, ensure that the overload protection for the transformer is properly sized and functioning. Overload protection devices, such as fuses or circuit breakers, are designed to protect the transformer from overloads. If the overload protection is not properly sized, it may not protect the transformer from damage. Consult the NEC to determine the correct size of the overload protection devices. Test the overload protection devices regularly to ensure that they are functioning properly.